We start, sir?
Yeah, we're starting at 10, no?
Yes, sir.
Yeah, nice. So good. Yeah, we can start at 10. Yeah, thank you.
Okay, sir. Thank you, sir. A pleasant good morning to all the participants as well as today's resource person. Today is day 4 and we are going to start our session 10 of AICTE sponsored ATAL online faculty development program on artificial intelligence enabled sensors and networks for 5G wireless communication. Today our resource person is Dr. Sibiraj B. Pillai, professor from Electrical Engineering Department of IIT Bombay. And today's title is Understanding MIMO Using Software Radios. I request Professor M. Sweetline Sonia ma'am to introduce our resource person.
A very good morning to everyone. On behalf of Department of Electronics and Communication Engineering, Mahendra Engineering College, I am Sweetlin Sonia, Assistant Professor of Electronics and Communication Engineering. Take this opportunity to welcome our resource person and all the participants to the session 10 of 5-day FTP on the topic Understanding MIMO Using Software Radios. And today we have privilege to have with us expert from the field of education who shall be reflecting on the topic of the session. Dr. Sibiraj B. Pillai is a professor from Department of Electrical Engineering, IIT Bombay. Graduated from Model Engineering College, Cochin, he obtained his M.Tech from IIT Bombay and postgraduate diploma in Communication Systems from EPFL, Switzerland. He did his doctorate in Computer Science and Communications from EPFL, Switzerland. He has also held a position as research fellow at University of Melbourne, Australia, and also worked in the telecom software industry. He has authored and co-authored 50 plus research articles in reputed journals and conferences. Dr. Sibiraj B. Pillai has delivered so many invited talks on workshops in various engineering colleges. He won the Australian Early Career Researcher Award for Excellence in Communication Theory in the year 2009. His areas of specialization are fundamental limits of communication systems, information theory and its applications, compressed sensing, stochastic modeling, resource allocation problems, interference channels, relaying and broadcasting. With this short note, I would like to call upon our resource person, Dr. Sibiraj B. Pillai, to enlighten us with your words. Sir.
Yeah, thank you. Thank you for the kind introduction. Yeah, good morning to all of you. I should give a prelude to what I'm going to do and say. Actually, I was this entire week I was down with a severe throat infection, and there was this all this kind of pandemics going on, right? So I had to get tested, and the things are all okay. So it's the first day I'm coming back to office, and straight away to this. And then I realized, okay, it's just that till yesterday, whatever I was speaking, people could not even make out it was my voice. It was as if someone else was speaking. Today it seems to be better, luckily. So I will try to tell something that I know about MIMO systems. So let me just switch on my video. I hope it is available. So you can, yeah, so you can hear me well, no? Dr. Panla, can you hear me well?
Yes, sir. Yes, sir. Audible, sir.
Yeah, because I have not been using these office things for a while. Okay, so I'll be slow and I'll be steady. Otherwise, I'll hurt myself. I cannot stress too much on my throat at this point of time. But I'm open to interactions and discussions. So if any of you have a question, etc., please stop me and ask. So this is I will say, much more informal session. Of course, if you want to talk about, so Dr. Panila, can you allow me to share the screen? I'm sharing the screen from this alternate place.
Yes, sir. Please.
Two machines, and I need to run software radio on the second machine. So I'm trying again. Their screen. Allow. Okay, so thank you. Yeah, it is being allowed now.
So your screen is visible, sir.
Yeah, thank you. Okay, so actually I was not planning to have slides or anything like that because too bored of all this just flashing slides and showing this and that. And turns out that a large majority of the audience out there, particularly in FDPs and other things, people look at the slides and people kind of enjoy, but not much goes in. That is a reality that I've realized over the years. So when I agree to an FDP or some program like that, it's more about interacting with people rather than just flashing slides, which we have umpteen, and there are thousands of slides one can just flash and show you. But that is not the purpose. The purpose is to learn something and to learn something from you, at the same time tell you something that you can try and use on your students. And overall, I think we should do a much more proactive way of teaching and learning these subjects, if at all we have to maintain any interest or retain the interest of students in these courses. As you can see, your FTP's title itself is about artificial intelligence, this, that, and others. In fact, I've given some talks on such programs as well, but there also people just look at those black boxes of neural networks, and we have enough results to show you, look, it works this way and that way. But what more? Is that what we are going to tell our students? Okay, here is a black box that can do things. I mean, that they really don't need our help or anything like that. Rather, we should try to tell what is inside some of these topics, what is the real pressure of learning these topics, etc. Go back to the fundamentals, and that can help overall reviving the interest, particularly in the onslaught of this artificial intelligence and so on, except by what Google provides, a lot of utilities and Python's utilities. Many of them, they don't even know what they're doing. Okay, so with that prelude, let me just show some of this. So I didn't have much slides, but then I thought maybe there should be something that you should be looking at. So I put a few slides from one of my previous talks. I just show you that. So I've been doing, so let me just show you some. Show you that. So I just made something straight away now. It's the last 10 minutes actually. So what can I do? Okay, good. Okay, here is what we have. Actually, these are like running things. Okay, so let us move to the. Okay, so that's the rough idea that we are going to do. We will have some facts and fundamentals about communication, very basic, so that at least there are a few pages that we have to discuss and talk about. That's a primary thing. And I'll just talk about software radios, modulation, demodulation, etc. And then topic of MIMO. I will see if I can explain to you using the software radio approach. And this approach can cut a lot of ice if you use with students and others. In fact, this is not just an educative tool. This is actually a very practical tool that we actually use this to build MIMO systems and OFDM systems, etc. on live, and then run it on the air. Okay. And then I put some blank because I was also planning to do a little bit of FDM part, but it looks like no, depends on your interest, and we'll conclude. So that's the rough plan. I'll give you some context. This picture I like to flash often, and just to contrast between the people. Anyone in the group can identify who these people are? Feel free, just switch your mic on, and you can identify these people.
Sir?
Yeah.
Mark Cody and Shalom.
Yeah, so these are Marconi and Chanel. And so they are well known for their contrasting way of doing things. In a way that if you look at Marconi, he won the Nobel, Shannon won the Nobel. So there is a lot of contrast between that. The first one is a real engineer who actually grounded out and built things. Second one is much more than an engineer. He could actually make much sophisticated things like that artificial intelligence. The first artificial intelligence machine is actually the one that you're seeing there, the mouse in the maze program, which he built entirely by hand and tools. So that means he's a real engineer, but he was a mathematician too. And it was a unique blend which has made this field progress in the last century. In fact, this developments done is now more than a century old for Marconi and actually almost a century old for Shannon. But still, they are so relevant. In fact, Marconi started what's called came to know what is to be known as radio sciences. Though Marconi was all about engineering, there was almost no science per se in what Marconi has done. He built those things, but then when it comes to Nobel and others, it is for the sciences that he won. Whereas Shannon is more credited with what is we call telecom technology. So you can see one is a sciences man, the other is a technology man. Turns out that's exactly the opposite. Marconi built technology, Shannon built sciences. But the contrast is that we use it in the opposite sense. In particular, he first guy was using antennas, coherers, oscillators, analog radio later. Initially, he was talking about telegraphy, things like that. Whereas here, we used a lot of math tools, entropy, mutual information capacity, digital radio, digital computer. All of them came through the same route. And if it goes back to the work of Shannon in the 30s and 40s. Okay. So one way to understand both of them is that when we teach or when we learn about radios, we take the Marconi way. We like go to the lab, make people build transistors, transformers, and coils and others, build the radio and let them transmit and receive. I think nowadays it's very extinct. No lab, even we have only 1 or 2 sessions here, but other places do not even do that. So it's almost like outdated. What Marconi has done. I don't know whether people even nowadays know what a radio is once they have their mobile phones. And on the other hand, this Shannon's stuff, unfortunately, we do not cover that also. If you look at it, we will ask them, teach them what is h of x, h of y, this, that, etc. Calculate some numbers and probabilities and write down their math questions. And just like your high school math questions, give them some questions that they can answer, which is not really education. It's more about just testing whether they can solve problems or not. Okay, so my opinion is that we don't do a good job when it comes to either Marconi or Shannon in today's curriculum or even the curriculum in the last 50 years. Nothing properly has been done. And there were a lot of limitations. I'm sitting in India, we had problems about doing things. We could do minimal with transistors and coils, etc. Whereas the other part, I don't think there were enough people in India who were doing high quality stuff that we could teach and we could tell people what it is. But this is all changed, particularly with the mobile phone and associated devices. Everything is accessible to everyone. So we should also be doing things which are at the state of the art, and we should also teach them. For example, how many of us teach in today's telecom technology or communications or what's our field? How many of us teach, say, something called polar codes? So this is an amazingly simple way. In fact, it can achieve Shannon's capacity, and that has been among the major breakthroughs in the last 10, 15 years. But nobody in the Indian academia or Indian industry even handful of them implement it for their purposes, but they don't do any work on it. Okay, so this is all can all change if with this ideas of software radios, we can actually go back to this Shannon's theory, whatever he has come up with. So where there is a source and the symbols which are transmitted, and there is this there's a channel, which is this noise source, and then the receiver and a destination. So this is essentially the picture taken from Shannon's what is that? His famous celebrated seminal paper, and he has even named it Figure 1 in communication systems. The figure is taken from Shannon's 1948 paper. And then Shannon used this model to come up with terms. For example, in the very well-known wireline case of telephone lines, that's where he was interested in. Primarily, he came up with this formula. We all teach this formula perhaps without completely knowing what it is. What is this formula? And we end up making people compute this left and right. Okay. But what is more than a formula, a math quantity? This is actually an engineering number. This number is something that we should strive to achieve. And for certain systems, polar codes, LDPC codes, there are practical schemes now operating very, very close to this. So Shannon's numbers are not just numbers to guide you, but these are numbers that you should try to go. So it is like here is a highway with a speed limit of 180 kilometers per hour. And Shannon is telling you, look, go near 180 kilometers per hour. It's not saying that, look, this is 180, so please do not go near that. The Shannon is telling you, go as close to that. That's possible without any accident in the way. Okay, so this is so there was a lot of optimism. Shannon's this formula. A lot of people, particularly in the US, Europe, Israel, etc., they all followed this and tried to get to schemes which reached this, and which culminated in this, let's say, last 20 years of coding theories advances. Any questions? Feel free to ask, even if it's philosophy. Absolutely feel free. Okay. Okay, so the idea of this whole thing, Shannon's, was to discretize the model. So here is a continuous model in time, and then but you discretize, you get with the samples, and then you form what is called this code book at the transmitter, and then at the receiver you receive a lot more values because of this noise addition. So you get a lot of values. A certain group of values, you say that, okay, if you get this group, the first group, sorry. So this is not here. If you get the first group, you tell the first message. If you get the second group, you tell the second message, and so on and so forth. And this kind of decoding rule. And in this case, so-called Gaussian channel, it becomes what is called a minimum distance decoding rule. So all these vectors here are closer to the first code word than any other. That's the idea. So you compute the distance and pick the one which is closest. And then you can also have so-called power constraints to say that your power should be within, or energy limits your transmission power, etc. You can put those constraints in and then work out what is this number and then try to get to that number. And that is what, let's say, post 3G, most systems were trying to get close to what Shannon has been predicting, at least a fraction of it with a fraction less than 0.5, let's say. Okay. Okay, so now we can visualize all this picture that Shannon has provided by doing something like this. This is a software radio picture. Picture means this is how it's implemented in software radio. And SDRI is for software defined radio. And then such a Shannon's picture. I mean, I'm a cut down picture. It's not the complete picture that Shannon has used in the previous thing. I'm not telling you, for example, how you form this code book, etc. in this setup. In fact, I'm not even using any coding in this picture here. So how many of you are familiar with this software radio tool called GNU Radio? Anybody heard about GNU Radio? Hello. Have anybody heard about GNU Radio? Nobody is talking. There are 60 people. Nobody has heard about Gene Radio.
Yes, sir.
Vijay has heard about Gene Radio.
Yeah, sir. We know the
Have you used it?
Gene Radio. Yes, sir. We use it a little bit.
Okay. Yeah, good, no problem. I mean, a lot of people have not heard about it, but so Tamil Russians saying no, that's fine. So if some of you have used it quite a lot, then some of the things I say may actually look as very basic. Of course, you can do much more complicated. We actually do complete end-to-end transmissions over there using this stuff. Here, even in my room, there are some facilities to do that. But I'll just walk you through slowly through this tool. The reason being that, okay, it's completely free tool. This is an open source thing. You can be part of the development also. In fact, some of our IT Bombay students did contribute to the blocks, particularly filter design, etc., which ships with the package. So it comes with standard Ubuntu or Linux repositories. I use the Ubuntu version, but it is also available in Windows. So you can, I'll type it here if you have not heard about it. I'll type it on the chat screen. This is gnuradio.org. Just go there, download, install whatever version you like, and you will see the power of it. In fact, I use that in all the courses that I do, from information theory, wireless communication, digital communications, signal processing, everything. I use this particular tool. It is much more powerful than MATLAB, I will say, because this gives a kind of a real-time view, and you can actually connect it and very easily to other devices and run it through an air. You can actually build a complete end-to-end mobile system in a very efficient manner once you buy the hardware also. But this is just the software, gnuradio.org. We will only use the software. I can show you the hardware part if you're interested in to do some of the experiments. So our idea is to understand, if possible, MIMO. I'll try to get you there, so that all the jargons and all the big things that people speak about, we can just understand. These are just plain high school mathematics and nothing more than that. Okay. If we really understand, but we have to really understand the communication and underlying engineering issues. For example, let us understand this block diagram, and then I will go and do this block diagram in GNU. Okay, I'll give you some basics, and then we will go. I should have a watch for the time. Okay, so okay, I think it's till 11:30, no? Dr. Panlada, time till 11:30, right? That's what we are going to do, right?
Yes, sir.
Yeah, so I will do, I mean, just that I don't want to stress myself also faster and more. So we'll do the minimal things, but I think there are a lot more experiments. If you're interested in, you can call me. I can send you some videos where we do this higher things that you can work and teach your students also. But this is really something, if you are in the industry or anything, that's also people are doing exactly this. Okay, so it is not just academic interest. This is real engineering interest. So what we have here, let's go through this block and try to understand this. So what we have here is there is a random source. So random source, you can think of a file with random values. It can be video, audio, anything like that. But here I'm mimicking with a random source. Random source because it is compressed video, compressed audio, etc. So it will more look like a random source. That's it. And then it goes to what is called this PSK modulator. So PSK, if you all remember, it is like one of those e power j theta, where theta n, let's say, and theta n for the n symbol. So it is like on a circle, you mark so many dots and take the real and imaginary value of that circle, and that is what you will transmit. And then you send to some channel, and then this is your receiver, and then you put your output to some scope sync, etc. Don't take these things down. I'm just using this as just an example. In fact, this is, as you can see, this is an old block. I'm just using just to show you that I'll do a new version of it now. So what is then GNU radio? This is a GNU radio flow graph or a software radio flow graph. So what is it giving? It is giving you these blocks. So for example, here's a scope. This is a time scope. This is nothing but an oscilloscope. So instead of a real oscilloscope, you take this sync, what so-called sync, and then use it. So it will act like an oscilloscope for. So you're mimicking an oscilloscope. This is very powerful action. This is an FFT sync, which means that it is a frequency sync. So it is a spectroscope. So instead of a lab spectroscope, you just connect this block, you will get the spectrum of the signal that is coming out of that. Similarly, if you want to put a channel model, just get this channel model block and put it there. Then there are several blocks which are customized and available. You can build your own blocks also. The entire code is free. The underlying building blocks are available in C++ or Python. So you can change if you want all these things. And there's no, nothing opaque. Everything is transparent. You can go look at it, change what you want, use it for whatever purpose you like, right? And this is not true about MATLAB or any of the other machines, any of the other tools. So that's why in here in our institute, electrical engineering, we use for many labs and teaching purposes instead of MATLAB or other tools. There is also LabVIEW and other tools. Instead of all that, we use this open source thing. And now it has matured to be a powerful. Initially, we also struggled to make these things, help files were difficult, etc. But now we use it because it's quite standard and available. We have enough expertise to do that. So typically, how do you get this thing is we just go here and as you can see, there is this, once you install, you get what is called this GNU Radio companion. So okay, so where is that? Okay, it is gone. Don't worry. So this is like, if you just type GNU Radio, double click after installing, or in Ubuntu you can type GNU Radio companion. Right, or just go here and GNU Radio. Then this picture will come out, and just click on that, and then once you click on that, I've already clicked this, and something like that will open up. So let me just take a new file. So some blank canvas will open up like that for you. So my initial idea, I was telling Dr. Panlada was, each of you should be able to install it and be ready with it. Because I use this for some of our industrial coaching, because we do industrial training for some of the big telecom industries in India, particularly people who work on the hardware and other things. So we do, and we actually use this. Build it. Okay. Extremely powerful.
Sir?
You can hear me, no?
Yes, sir. You are audible. The screen is also visible, sir.
There were some network issues, I think, but maybe just temporary. Okay, so here is what we have. So our job is that we are going to come up with such a program, and I'm going to show you how do you run this in a GNU Radio. So if you can quickly install GNU Radio on the fly. So for example, if you're on a Ubuntu machine, just sudo apt install the command that I have written here. We'll do it in a minute for you, okay? If you're on Linux machine, you can just install GNU Radio. Automatically, it will get an install. In a minute, it will be done. And if you're on Windows, it may require a little more work. But nevertheless, we have many of our students install it on Windows also without much problem. But it will take a little more time. Okay, so you will download and then install, etc. So I'm not insisting on it. Please work with me. I'll show you on the screen how things are done. But very, very important is that you have to ask questions and you have to understand each step. Otherwise, it will be kind of just a movie watching, perhaps a very boring movie, and you don't like it. Okay, understandable. So let us see, and feel free to ask. This I insist on. Any class, industrial or otherwise, please ask. Otherwise, you won't learn, I'm sure, because something which is going through my mind has to reach you. Then it has to be, there has to be a to and fro. Okay, so please ask. Okay, so what am I going to do here? First, let me just show you the power of this by just starting with a simple program. So I'm going to take, imagine you are in a lab. The first thing you will do, you take a function generator. So for function generator, so you just type Control F here. So Control F is what the finding function will. Okay, or you can just come up with the view, and then you can show also find blocks somewhere there. Where it was. Yeah, so you can click to one of those find blocks. You can see that and click there. It will show you this window on the side. So you can see it's a lot of blocks available. In fact, for coding, for channels, for OFDM, this, that, etc. You name it. Any of this communication that MATLAB or other services are providing, you will find an analog. In fact, more here. Okay, and the power is that this is completely free, and we all contribute to it also. Okay, so let us say source. So we just take a source, and then if you just type source, there will be a lot of sources which will be listed here, and we take something called a signal source. So this signal source is a function generator. I can make it a little bigger so that you can see. So this is a signal source. And if you double click it, it will show what is inside that. So it will say output type. If you look at it, it can do float, integer, short, byte, etc. So that means all data types. So it's software, so you can generate essentially float means a 32-bit and one 32-bit float is 64 nowadays. These are 64-bit machines. So it's one 64-bit value that you get. Complex means you get two 64-bit values on real part and imaginary. Integer means a 32-bit thing, and short is 16, byte is 8. So you can see multiples of 8. It will come there. And now, what is that? So this is there's something called sampling rate. The sampling rate is something which determines, because digital systems, so we have to run it at a sampling rate, and we can choose a value. Here you can see it is 32,000 samples per second. That's just a number. You can change it to values that you like. And now what is the waveform here? So there's array of waveforms: sine, cosine, square, triangles, sawtooth. If you have used a function generator, then you will be clear what these things are. So we'll just work with the cosine waveform, right? Amplitude, offset, those things are all clear. We can play around and change them. Okay. So that's our source, and to see them, we have to actually use what's called sync. So if you type sync, there will be a lot of syncs available. In particular, what we are looking at is a sync with a Qt. Qt is a graphic interface. So Qt is a kind of a programming language that you can write these graphic interfaces on. So you take Qt as a library actually, and then take this, let's say time sync. Yeah, just take this time sync. So it is there. If you double click, it will come, or you can just drag and put it here also. But since my thing is very bigger, I made this thing bigger, so it may go and hide some. So you just drag and paste it here, and then you can simply connect the two. So this is the power of the thing here. Okay, so how do you connect the two? You just connect it here and connect it. That's it. So now this entire program is generated for you. If you run it, you will start seeing the output of this thing. Okay. So what is the difference between such a program? Okay, of course, the graphical interface and something that MATLAB or Simulink provides. Okay, so the difference is that, of course, this is, you can easily plug and play with hardware. That's one thing. To some extent, MATLAB Simulink also supports that. But here, one thing is that though this is running completely in software, it can interface to the hardware. So to interface to the hardware, we need to bring in what is called a speed block. This is essentially the clock of the system. You can think of it as a clock. It's called throttle. So throttle is a speed maintenance thing. So it is like a pipe which connects the input and the output. And this fellow will interact with the computer. So if you put a very high throttling speed, what it does is that it will go and steal a lot of cycles from the your computer's processor's cycles and due to GNU radio. So if you want to run a program faster, you can put at a high throttle rate. And if you want to run slower, you can put it at a low throttle rate, etc. But here I have used the speed to match the sampling rate because at sample speed should go. Okay. Now we can just save this. Let's save this as just put a folder set. And just give some name. And there are Python names, so you should be careful about the name. Just give some name which doesn't conflict with standard variables. Don't give GNU radio, etc. So you just something like first program, which doesn't conflict with Python names. And now if I run this, what you see this, there is this window in which you are seeing this times the source that we have generated. So let's make it a little bigger. Right. So you see the power of the scope is that you can now kind of zero into the various portions. And you can look at, this is the real part. The pink is the imaginary part. And right, so it is a function generator output on the oscilloscope, as simple as that. But this is powerful for the reason that you can also look inside and see what is happening. Because what is really happening is that this is a digital signal, though it's a underlying sampling going on. So you can see the sampling by just putting this. So if you middle click, it gives you a lot of options, or you can right click and choose also. So here, if you just say that what you want is that there's something called stem plot. So just take it. So now you can see that you see the samples. So now 1 over 32 or the 32K is that the space between any two samples here is 1 over 32,000. That is the meaning of that sampling rate we have given. So these are the samples, and these are the kind of the real and the imaginary parts of it. Okay. So let me now ask people if is there any question on this? Also gives me some breathing space for my throat. Is there any question on this? Anything that is unclear or you like to know details, feel free to ask.
Sir, good morning, sir. This is Sindhu.
Yes, Sindhu, go ahead, please.
Sir, how you decided the sample rate here, sir? You are saying 1 over 32, right?
Yeah.
Whether it is fixed or this can be varied.
Okay. So please keep on asking all that questions. These are very nice. See, for example, here I can put here this of 32,000. I can put one more, like 320,000, okay, 320K. So this speed is something we can change. Okay, and so it is up to you to design the thing. You have to design this step. Now, Sindhil has brought a very interesting question. The question is that it will go back to our slide, let's say the slide that we have here. We can ask the question what is the bandwidth of this communication system? And that is intimately connected to the so-called sampling rate that we have connected to the system. I will do the connection, Sendil. We continue, I will make that connection. For the time being, we just need to put the speed that you like.
Yes, sir. Thank you, sir. Thank you.
Okay. Yeah, good question. Next, please, more questions. Please come up with more questions. My take is that if you don't have questions, you're not getting it. As simple as that. Please ask.
Sir?
Please, Vijay.
Sir, if the sample rate of source and signal are different, then what happens if you change, suppose, if they have different values? What is the effect?
No problem. So, yeah, that's also a good question. So, a lot of such questions should be there because this is very basic we're talking about and first time you're seeing. So, there should be a lot of such questions. Feel free to ask. And so, let us clear Vijaya's doubt and at the same time make one step forward is by I also put a frequency sink. Okay. So, let us say frequency sink. So, this is a frequency sink. Sorry, it is a little below because I made the block very big. Okay, Vijay, I will answer the question using both this, then it will be much more clear. So I connect it to this also. And here also you see something like bandwidth is 320K. Okay, so we are seeing river here. So let us run this. Are we running this now? Okay, so let us run this, Vijay. So what you see is that so this is 320K. Unfortunately, what is happening is that the speed is so. Okay, so you can see that this is this. Ideally, what it should do is that it should show you this plus and minus 1 kilohertz. I don't know what happened to the fellow. Okay, so let me just go inside here and put this is complex. That is fine. So my icon is not being shown. Okay, so clear. Now it's clear. I'm sorry, I was not seeing this. So it is here. Just that picture was a little small. Okay, now you can see that the top part is nothing but it's a complex waveform e power j 1000 t. Right, that's what this waveform is. Sampled at 32,000, which means 1000. So it's 1K. So you can see it is 1 kilohertz. I was looking for the base of the thing. So you can see it's a 1 kilohertz waveform. Now, why are you seeing such a spike here? Vijay, why are we seeing such a thing here? Why don't we just see one height here?
Because we are saying the carrier frequency is 1.
No, because of that. 1K, see what is happening is that this is called windowing. You window this waveform to calculate the frequency, then you will have a problem with this width here. I can make it sharp by changing the window. So there are a lot of windows if you have learned this. So now you can see that it has become sharp. Okay, so it is just the effect of windowing. So all these DSPs that you have learned, you can try out in this in here also. So we'll just go back to the window, and so typically they use this black pen hats kind of thing. Okay. Now I'm going to change. So you see 1 kilohertz here, right? That is because it is. What is the width here? Minus 15 to plus 15. That is because 32 kilohertz sampling can take wave frequency from minus 16 kilohertz to plus 16 kilohertz. That's why you are seeing minus 15 to plus 15 here. Now, to answer the question, I'm going to change this number. So that number here, I'm going to make it by 2. Okay, so it's 16K here, 32K here. Okay, Vijay, this is what you were asking. If I change, what will happen? Okay. Hello, Vijay.
Yes, sir.
So let us see now. Yeah. So now what is going to happen is that the base here is now only from -8 to +8. And you are still seeing that 1 kilohertz here. Sorry, 0.5 kilohertz, right? Because your everything has now scaled down by half. So this number here is only used as a reference to give you the value. It doesn't change anything. So this is a digital, it's a computer-based thing. So it can use tell the value, it will plot according to that. So if you give here 10, it will replace 1 kilohertz in 32. So in here it will be 1 divided by 3.2 kilohertz. If you use 10, use 16, it will be 0.5. If you use 8, it will be 0.25, and so on and so forth. So it is just a scale. It doesn't change anything because everything is in software, right? It's a dividing number, simply changes in the display. That's all. But it matters. The sampling really matters if you use a hardware associated with this. Okay, it's very easy to use hardware. For example, the computer's hardware can be used. Like if you take an audio source and play it out, then you will see this speed really matters. I can show this, but unfortunately no sound will come because of this, the way these machines are. So let me just show you, play this song to you. And so I just take an audio sync. Again, this is a bit smaller, so I have to get this audio sync. Now, but it's good because it gives me some time to tell you about other things also. So audio sync, you can see it has a that saffron or the orange color here, as opposed to blues in this color here. The color is indicative. The blue is telling that it is complex. So these are complex values at the output. So we can convert everything to real. So if you just go there, just click on the complex, convert to float. So this is one real value. So only cos part, sine part will not come. Then it has to be matching. Very important, because whatever the computer pushes out from here, this guy has to read. So the blocks have to match. When one value comes out, one value should go in through this. So all these things have to be floating point. But in communication, we are more used to working with complex values. Okay, now I can connect this also. Now, such a flow graph, this is, I can hear the audio. Maybe I'll play out and you can see it's 1 kilohertz. So you just stop the other program. Right. Perhaps you're hearing a small spike, right? That is because you're hearing it, no? So this is a 1 kilohertz sine wave which is playing. I'm putting through a headphone so that it doesn't loop. So it's a very small sound, but it can play out through the audio. Okay. So you can connecting to hardware is extremely easy. All you have to do is that just take the corresponding block and then it plays out through the audio. In fact, my computer plays it through the headphones. Okay. So it is that simple to connect hardware. But the only thing is that when you have hardware, the hardware comes with its own clock. If you go inside, it will have the hardware card has various speeds. And then you have to match that speed. So then you have to disable this party here and connect it. Because 2 clocks, there has to be handshaking, otherwise there will be a problem. This is a hardware clock, so we just run it. It will work out like a charm. Okay, so those numbers, 32K sampling rate, etc., are just for the computer to indicate on the display what those values are. So if you put them correctly, you can make the correct, decipher the correct values. But the real speed of this is decided by what is this audio or the hardware which eventually you connect to it. Okay, so that's the answer to Vijaya's question. The hardware that you connect will decide the speed of the machine, and the sampling rate of that card or device that you connect will determine the speed at which you really run. Vijaya, did I answer your question?
Yes, sir. Thank you, sir.
Yeah. So are there more questions related to any of this? I'll otherwise remove this audio part. We don't need this. We can just go back to our. So this is not required. Okay. Okay. So that's our first experiment with Genie Radio. In fact, I could make a lot of fun experiments with that. In fact, you can mimic your telephone dials. We can make it sing Sarigama Padanisa by itself by using what's called a voltage control oscillator. We can generate AM waveforms, FM waveforms, all kind of basic level 1 communication systems. You can implement straight away and teach people exactly how it works. Okay, so as simple as that. But today our purpose is not to do that, but we wanted your topics, etc., is about MIMO and this, that, etc. So let us now go to getting a communication system, a real communication system, or mimicking or kind of modeling a real communication system. So we, instead of the sine waves, I'll take signal sources, data sources, and then I will generate this key question of what is the bandwidth I will address also. So let us write down our objective as to, let us say, generate, here I can write, sorry. Okay, so we want to generate a, let's say, 100 kilohertz baseband waveform per objective. So I have written this in the chat screen. So 100 kilohertz baseband waveform, let's say carrying, let's say QPSK data or QAM data. Okay. Let's say QAM data. Is this question clear to all? So we want to generate a 100 kilohertz baseband waveform carrying QAM or QPSK, if you want to think of it in a slightly different way. This waveform we want to set. Is the question clear to all? So we are going to use Genie Radio to generate this. In fact, I'm going to ask some of you to help me. Okay. Okay. So we take a new flow graph. So I'll tell you what to do. Take file, new flow graph. Okay. Just take this new flow graph. Okay. So I'm sorry, I'm going to ask people questions because I'm too tired to speak full time. So if you ask questions, it helps me to breathe a little bit. So who is going to tell me about from this? There is, I see many people here. Maybe alphabetics is fine. Aruna, can you tell me what is the first block we need to generate? We want to generate data waveform, right? For communication. Aruna? Okay. This is some knock on my door. 1 second. Okay. So nobody is speaking. Achila? Hello, Achila? Yeah, at least just say hi. Am I audible? Okay, Asha? Nobody seems to be this. Oh, these people have all switched down and yeah, Savida. Thank you, Savida. So signal generator, very good. So thank you, Savida. So please be So, so with the signal generator here, what we do is that we need a data symbols, right? Because we are using digital communication. So what we do is that we take a random source, right? That's the signal for us, random source. So because we need QPSK or QAM, how many random symbols do we need each time? How many symbols are there in QPSK?
4, sir.
4.
Need minimum 0, maximum 4. Maximum means it will only go up to 0, 1, 2, 3. So 0, 1, 2, and 3. Maximum won't be taken. So that's why this is 4. So now, if you look at the random samples, I can make it bigger so that you can see it also. So this 0, 1, 2, 3, one of the samples will be taken. Number of samples is 1K. So you can even make it bigger, no problem. So 10,000 such samples are generated. Repeat S means it just does that repetition. You can replace this by a file or a wave file or a song, and you can play it out also. Everything works out. Because for a computer, it's all just files, bits, nothing else. Now we want to convert this values. So it is like 0, 0, 0, 1, 1, 0, and 1, 1. We have read from this block. Now digital modulation, we want to convert this into, let's say, QAM. Okay. So what are the QAM symbols or QPSK symbols? Which are those? Let's say 4 QPSK. Which symbols are there? Or 4 PSK or 4 QAM. So we can, what we do is that the Genie Radio gives a very nice utility. It's like a simple map. Again, I have to make it smaller to get this thing. Okay. So this chunks to symbols. Just dimension is 1 because it is taking one input from the source. And then we have to give a symbol table. I will not worry about the scale. I will simply say -1, -1J. Right, this is on the -x and -y point, right? And then -1 plus 1J, 1 minus 1J, 1 plus 1J. I'm not worrying about gray coding or anything like that, right? Just simply these 4 symbols. So what the meaning of this is that when 0 comes, it will output -1 minus 1J. This is a Python style, so it is nothing but -1 minus J, right? E power minus J 45 degree. That you can think of, or e power minus j pi by 4. And each of them is e power plus j pi by 4 and so on and so forth, right? 3 pi by 4 and minus 3 pi by 4, etc. Okay, all clear? So these are nothing but the QPSK symbols. Right? And then what we can do is that we can, let me make it a little smaller so that I can have some space to work with. Okay, so now let us see the output of this. So the good thing to, I'll take a throttle. This is nothing but a speed control. Oh, again, it became smaller. So I take a throttle here. And then I also, this time I use what is called a constellation sync. Now I make things bigger. So that you can see. Okay, so what we do is that we connect, and we can just run this. I just need to save it, and so we already used this. That's a second program. Just run this thing, and these are our constellations for your QAM or QPSK, right? -1 minus 1J, and so the in-phase component is -1 or +1, and the quadrature component is also -1 or +1. Of course, this looks a little unrealistic, very clean, so you can just add a little noise if you want, right? So just bring a little add here. And then you can put what is called a noise source. So this is too noisy. You will see that it has a lot of noise inside this. As you can see, that's what is coming out. Okay, that's because it's too noisy. So I'll tell you, earlier somebody was saying, can we adjust dynamically this noise? Yeah, I'm going to try to show you how to adjust that. Just take a range. Again, went down. So we just pull this guy up. Next time I should drag it. I forgot. Okay, so this range, we can give a name of this variable. Just say noise variance. Okay, and the default value is 0. Stop value is 1. Step value is, let's say, 1 or something like that. Okay, then we run. So you can see that it has no effect on this. That's because I have not linked it. So I come here, put here the variable name, noise variance. Okay, now you see, if I change here, it will change dynamically on the fly. Okay, so no noise. Now we'll add a little noise. You can see what's this kind of the pictures that you will see if you work with QAM, QPSK, etc. And you can increase the noise, keep increasing the noise. Now you can see your signal is lost. Okay, so our purpose in the communication system is somehow reduce this noise and then get this constellations out. Okay, all clear? Any questions about what we did just now? Okay, so there are a lot of this utility. You can mimic real systems by just simply playing this out. But this does not meet our objective. Where is 100 kilohertz? We were talking about 100 kilohertz waveform, right? So we can do, let's say, to say the kilohertz, take a frequency sync. Oh, again went back. Hope it's not down there. Down. Okay, good. So I'll drag it. Okay. So let's connect the frequency sync. Before I click yes, what is the bandwidth you expect? I mean, this is where you should be able to think and tell me what is the bandwidth you will see before I click. Can anybody tell me what bandwidth will you see? Bandwidth is in this communication sense, because we are talking about random waveforms. So random waveforms, you cannot really talk about a bandwidth because the signal may occupy this, that, or whatever it is. But what we can talk about is power spectral density, which in some sense is an average power, so which is a very sensible thing. For example, I ask what's the temperature today. Of course, you cannot say an answer, right? Even the room that you're sitting or the place that you're sitting, there will be variations of the temperature, 31.1, 31.05, etc., etc. But when I ask a question, you say 31 degrees. So we understand on average sense, that's the value, which means there may be deviations, but that's the rough sense of the answer. Same thing here. I cannot talk about bandwidth of a random waveform, but I can talk about the spectrum, the power spectrum of the waveform, which is an average quantity. And that we call the bandwidth, that how much frequencies or how much band the spectrum is spread, we call it as the bandwidth. So anyone here sitting can answer me what is the expected bandwidth? Because our plan was to design for 100 kilohertz. If we know what will come out now, then we have a way of attacking the problem. So maybe I should keep calling names, or anybody who feel free to come forward. That's much better. Because I think this online, no? 4th day of the FDP, people will just click their link on and do household stuff. That's very usual. Nothing wrong about it, I would say.
Sir,
Yes, Sindhil, yeah.
Can we have it as a 400 kilohertz?
No, that is okay. No, Sindhil, how much will you see now is the question. If I click OK, this frequency, you can see here it's 32 kilohertz, right?
Yes.
So it will go from minus 16 to plus 16, and it will show the all of it. That's the problem. And so the bandwidth that where is my picture? Oh, there's something else down here. There's something else down here. Okay, so if you click here, what you see is a flat band from minus 16 to plus 16, which essentially saying the bandwidth is 32 kilohertz. It's flat across everything. So I can make the average higher and show you that that is how the band is. That is because we are using a kind of an independent noise, independent samples here. So then power spectral density, if you have learned your power spectral density, then you will see that the autocorrelation will be a spike because successive samples are independent. So the autocorrelation spikes, so power spectral density is flat, and that's exactly what you're seeing. So the bandwidth is all the way from minus 16 to plus 16. Don't look at the left side values. That's because the logarithmic scale, it's just a dB gain, that's all. So it's all high up there. Okay. Now I can add some noise here just to tell you how what will happen. You look at the value, now it's near about minus 35. If I add this, you will see what's going to happen. This value slowly goes up. Just that the scale is too small for that to show up. You can see it's coming down. Okay. So that's it's a small difference only in this case, so that's why I don't see much. Okay, it's just a 3 dB difference. Earlier it was 1, now I added noise up to 1 more value, so it's a 3 dB difference. Okay, so that's how the noise variances are in this system. But the bandwidth you can see is 32 kilohertz in this particular question. But what we want was a 100 kilohertz waveform. So as Senthil suggested, I can go here from, let's say, 320 to, so what was Senthil suggesting? 400. Okay, sure, no problem. I put 400. So third, 400. Okay. Now I run, of course, you will see from minus 200K to plus 200K, minus 200K to plus 200K, and it's flat. Okay, so we can make the average high just to see it's flat. Okay, Senthil, but the bandwidth now is minus 200 to plus 200. In communications, this is a premium.
Yes, sir.
100,
yes.
Should not go about it. So how do we make this 100?
Sir?
Yes, please.
Did you ask any question? I could not get you.
No, I'm interested in making the communication bandwidth 100 kilohertz.
Okay, sir.
How do we do that? This is a fundamental challenge in any level 1 communication. That there is a digital signal, I want to make it bandwidth 100 kilohertz. Which means that outside that minus 50 to plus 50, my power should go down to 0.
Go down to 0.
Okay. Yeah. So Senthil, how will we make it happen?
We can put a filter, sir.
Exactly. We put a filter. So what kind of filters can we put?
It may be a band pass filter since we want to have a range, or if we start from 0, we can go for a low pass filter.
No, what are we talking? Look at this, Senthil. This is minus 200 to plus 200.
Yes, sir.
So what filter will you put?
I could not get it clearly, sir. No, I cannot answer this.
No problem. Yeah. So what we should put a filter which will take from minus 50 to plus 50 and cut everything off. Right?
Yes.
Because it's only passing the low frequencies, we call it a low pass filter.
Low pass filter.
Okay. So how do we design a low pass filter and cut this thing off here? Okay. So what we do is that, so this is how, yes, Ranjana, Ranjan, this is an LPF. But how do we design that LPF and put it here? This is the key thing we are going to do now. Okay, so let us design a low pass filter. But the bandwidth should be 100 kilohertz. So bandwidth you can think of in the following way also. Yes, please. Who is this? Please
Can we go for an integrator?
Yeah, we can do that. We can do that. It's a low pass filter, so we can come up with low pass filter integrators, etc. There was some other person asking a question. Feel free to ask. Okay, if no, let us go. So let us take a filter. So we take, so there are many filter blocks. If you just type filter, there will be a lot of filters will come. This filter, that filter, etc., etc. So we just take a interpolate. There are root rays, cosines, this, that, etc. But just let's take an interpolate. I clicked again. It's coming by a habit. Okay, so let's bring this fellow here. Okay, noise is not very important for us. Maybe I'll put it here. You can take the data and I'll do this filtering. Then I'll throw it. You can do it in any order that you like. It's not a problem. These are linear systems we are talking about. So let's cut this and paste this fellow. Okay, so what I was telling is that when somebody says the bandwidth is 100 kilohertz, you can think of, actually it's equivalent to 100 kilo samples that I am transmitting a second, which means that 100 kilo symbols, that here that we have QPSK or QAM symbols, 100K QAM symbols every second will go out. And here I have set the speed at 400. So which means that 100K samples should come out of this picture and then converted to 400K. So first thing I put an interpolation of 4. Okay, which means that every sample here will be replaced by 4 samples. In fact, here the interpolation simply means you put 3 zeros in between each 2 samples. Each successive samples you put 3 zeros. So that 100K samples are taken here, 400K samples are delivered to here, but you added 3 zeros, so essentially nothing there. And then you put a filter. And that filter you can put is, what is the ideal low pass filter in time domain? Who is going to tell me? Ideal low pass filtering frequency is simple rectangle, right? So let me ask. Yeah, Ramesh, thank you people for answering. It's great, and please do participate, because I don't even know some of these people are sitting or not. So I'm afraid now to ask also that people are not there.
Can we go with the sine function, SINC?
Yes, Senthil. Very nice. We can use a sync function in time domain because it is a rectangle in a frequency domain. It's a sync function in time domain. So all those theory that you learn is really, it's not theory, it's real engineering. We use that. Okay, so I'm going to tell you how to use that. And that's another place where the real power of such GNU radio or this software radio platforms come in, is that you can use Python and to some extent C libraries, etc., to do the coding. But directly in the flow graph, you can use Python. If you're familiar with Python, there is something called numerical NumPy in Python.
NumPy, sir, it will be
NumPy. So you can just import, so that I can get the sync function directly. Again, I click. So I can import here. So if you just do, if you don't import, it's okay. You can still calculate using your sin x by x in MATLAB or Octave. Just cut paste those values here. you will get the filter. So once I do this, I can get all this utilities. So I simply here say np.sync, and then I just simply give space. So this is just about a few values that I'm giving, and some values. I mean, I can give from -3 to +3, which means 6 symbols. Each symbol will be 4 times divided. So I will just break it down to. So if you just click on it, you will see that it is nothing but a set of values that has come. So if you click on it, you will see that just a vector of values. And this vector you can generate using MATLAB, Octave, and just cut paste those values here also. But the advantage of GNRD is it can directly call Python routines. So I just in one step here I have got the this particular fellow here. Now what is this filter? You want to see this filter? Maybe I can show this filter also. What we do is that instead of the random source, I just take a vector source. Oh, it again went down. So I just take a vector source. Just give some value, that's it. You can give, let's say, something like a 1 plus, oh no, this is not good. Yeah, I thought I should, I can show you quickly what is the output here, but 0 is not going to map to anything here. Okay, so we will do, just put a 1, yeah, 1 plus. I put a, let's say 100 zeros, maybe 50 zeros good enough. So it's like an impulse. I just have 1 and there are a lot of other values, and just instead of this 2, so I just don't put this, but rather put this. Okay. So now if you look at the output here of this time sync I need, just put a time sync also. Then you will see what is the output. And once an impulse is put, it's exactly the filter's impulse response will come out, and we will be able to see that here. So you can now verify that, and you can see that. So I can stop this code. Stop, go inside, and you can see it's exactly the sync that we have designed. From you can notice that the sample values which have come. Okay, that's the sync we have designed. Okay, so it's about giving these values. I've taken from -3, so that is first cycle, second cycle, third cycle, fourth, fifth, and sixth. So 6 cycles I have used. Okay, so you can put your filter here. It's a sync filter. Just put it here. So and now we can go back to our waveform. What was that thing? Sorry, this is view. Don't hide disabled blocks. So we just disable this, enable this, enable this. So we just go back to where we were. Okay. Some jamming happening here. Okay. So now I can show you what happens. Let's look at the bandwidth very closely. This will be exactly the design bandwidth that we are after. So this is the QPSK waveform now. The time domain QPSK waveform. Constellation is somewhere here, but the constellation is gone because we are using interpolated values here, right? It's not just QPSK values, but they're interpolated. So the constellation is completely damaged, which is okay. And then there may be noise also, but this is the frequency output. You can notice that from -50 is here, +50 is here. After that, it falls out. And our low pass filter is letting a little bit pass outside this. That is basically because I used only -3 to thing. So if you use, let's say, -10 to +20, and then I put this on 21. 20 times 4, 81. So 51. Then you will see it will sharper. Now if you notice, you will see that our design is exactly matching what we are trying. That's a 50 here. Okay. So more the length that you take in time, you can actually get to get your waveform to be the exact frequency very much. So this is how the spectrum will look like. So this is how a real communication system develops its output, except that instead of using the sync, people use what is called raised cosine filters. If you take any theory book or anything, you will see that this is nearly approximating a sync with a better fall off, okay, in time domain. Okay, so that's the waveforms, QPSK, frequency, and this design exactly matches what we want, 100 kilohertz. Okay, is it clear to everyone? Are there any questions? Please ask. Anyone, feel free to come. Even if it's just a discussion, feel free to come forward and ask. Okay. I'm not clear because nobody's asking questions, so I'm a little confused myself. Typically, I get a lot of questions when we do this thing because it's really hands-on stuff. Okay. Yeah, please. Go ahead if you have a question. Okay. So now, I'm slow. It's okay. How many number of taps is used? So this number of taps here I can use. So how did I choose? See, what is happening is that so this depends on the interpolation factor, etc. So in every symbol, we are interpolating by a factor of 4. So 1 input, 4 output should come out. So here I used -10 to 10, means there are 20 symbol periods that I'm using. 4 times that is 80. So I'm using 80. The 1 is just because the 0, the middle sample, I need just 1 extra. Even if I use, let us say, no, this 80 is because the way I'm generating, I need 81 samples, correct. Whereas if I use, let's say, -20 to +20, then because now 40 are there, so 161. That 1 is for the central sample. So that's the number of taps. The number of taps is 161 here. And we can make the design. Typically, -5 was good enough. This is 10, so 41. Okay. Now let us do the final purpose of we didn't talk about MIMO at all, right? We talked about everything else but MIMO, which is not good. So let me show you how can you do the same program here. So I have actually did this for this other batch that I was taking a class for. This was done live on the floor, but people worked with me. So everybody also did this code. And there you can see that there are multiple such blocks. So there are the same kind of data blocks that I used. Instead of the FIR filter, I used some other filter, but this is essentially generating those waveforms. Everything is running at 32K. And then MIMO, the same system, there are multiple inputs and then they get multiplied by a matrix. That's the difference, right? And then you can have multiple receivers. So let me just run this and show what the output looks like. So this is a 2x2 MIMO. I have 2 streams of data that I have input. The red stream of data and the green stream of data, both QAM. But the red stream of data nearly went without much problem, whereas the green stream of data, they got all kind of, you cannot make out which one is the thing. It's all lost kind of idea. Because you see one constellation, you see a rotated constellation, and you see something in the center, etc. So you send two data streams and they kind of interact with each other, things are lost. Now in MIMO, what we do is that we do some pre-processing. So if I do the pre-processing, then for example, after pre-processing, the data looks like, so same red data and the green data, I'm going to do some pre-processing, and post pre-processing, it looks exactly like this. So you get back your original QPSK constellation by doing pre-processing and post-processing by simple elementary matrix multiplications is what we do. Suitable matrices we take and we multiply. So in fact, we can realize any complex MIMO system on this GNU radio setup by simply, as I'm showing here, you can actually make somebody build that entire thing from scratch and understand precisely what is MIMO, what are the physical constraints in terms of, let's say, bandwidth, power, and all this kind of thing. You can also teach more complex things, like if you can change the power between antennas, or you can control the power between or the transmissions to kind of get both the signals here. For example, the green signal has a lot of signal to noise ratio, red signal has much less signal to noise ratio. You can control the power or this antenna directions and etc. to kind of make them both equally good. The green will become a little poor, but red will get much better. Then so you can do a lot of this experiments of power control, a lot of things. So all these things can be done if you systematically generate this and work through people. Not only you will learn it completely, but any student who is doing MIMO will be able to completely run through this flow graph here. In fact, time permitting, and if you had the facilities of GNU Radio at your machines, my plan was to make you do this one by one and explain to you each of these blocks. This contains all the details of communications, including power, bandwidth, reception, match filtering. Everything is done inside in one way or the other. But for the time constraint, also because I can't push with my throat, and plus also it's also a response-based build-up. People ask more questions, we do more things, and once you do something, we'll do much more on top of that. That's the kind of idea. Okay, so but I hope I have given you a sense of what this software radios is about. In fact, we can actually do. See, this is where I stopped. This was all this kind of Shannon's theory we can show there about this numbers and bandwidths, all these things we can do. I did not show you some of these details, but you can do, for example, many of these normal wireless systems and power control, etc. You can do exact demo, end-to-end system, how OFDM works. In fact, I have some. Oh, it's on my, sitting on my room is some of this OFDM over-the-wire systems, which we built just by using this software radio tools and then connecting through the air. Okay, so you can, the entire theory of MIMO, that how can you break a matrix channel. So it's all about a matrix, how you break it down into multiple scalars. The base of MIMO system is about breaking this multiplication. Which in this picture you can see that, or did I close this? Where is this? In this picture you can see that the matrix multiplication, this 2x2 matrix multiplication damaged one of the data completely. Whereas by doing this pre-processing that I was showing in this slide, you can actually break it into different things. It's like a complex highway with a lot of vehicles. You can kind of separate down to, okay, here is a line for lorries, here is a lane for cars, here is a lane for cycles, etc., etc. And they don't interfere with each other and can give different quality of services to each of them. And like here, so unfortunately here the greens and the reds, all they got tangled, and that's why you don't see the QAM here. But doing MIMO processing, we can get them separately on the lane. Not only that, we can provide different quality of services to the lanes without affecting each other, etc. Okay, so that's the power of this theory. And I encourage you to go through this GNU Radio and build it up. Maybe it will take a while for you to do the initial steps, but it's worth it. Not only that, the students and others will also appreciate and understand the details, how it works, in fact, leading to new developments and things like that. So here is, for example, here is our lab system in IT Bombay, where information systems and radios lab is something we have developed, and you can see all this software radio boxes, and they run directly from the GNU radio based program. There's a USB connect. Sorry. Some of them has USB connectors, some of them have Ethernet connectors. You run the program, and then it goes through this antennas, and you can listen at these other places. So you can experiment the OFDM, MIMO, all kind of things that you can do, and that too real. So it is a proper convergence of the theory, practice, engineering, state-of-the-art development, or even going back all the way to Shannon, let's say 60, 70 years back. All of these things can be done now completely end-to-end. And that is why this tool is something you should spend time and learn it. Okay, so I will stop here, right? And that is the time, I think. I hope it was useful, but I'm open to questions if you have questions.
Hello, sir.
Yeah, hi.
Good morning, sir. Very informative and brilliant session, sir. I liked it. First time I have seen how to use GNU radio with software-defined radio.
Yeah.
Actually, I'm working with the cognitive radio. In cognitive radio, various dynamic spectrum access algorithms, etc. So those algorithm I'm developing using MATLAB. Now,
Yeah.
thing is that just I'm studying the algorithms, right? Now, thing is that if I want to implement this algorithm using this GNU radio, how should I go ahead?
Yeah, so if you want to really do some hardware, then you need this extra boxes, or there are also this dongles, small end devices that you can buy to receive, etc. So if you are interested in really testing out how something works in practice, then you should buy this little dongles that you can plug to the computer and then use the hardware to that.
Okay.
But for those algorithms, etc. See, the problem with MATLAB is that the development is fast, but it makes you blind to what is underlying. I mean, I've been noticed that some people may not even will not be even able to explain what they have done, because the MATLAB code gave them some answers.
Okay.
So I will suggest, okay, look, this is not in a way pushing or anything, but just about encouraging. Python is a much better tool. If you use Python libraries, almost everything in MATLAB is also available. But
Okay.
plus, you can also, when you write the code, or even C for that matter, is much better because it makes you aware of what is really happening, rather than giving a black box answer to the question. So try Python, and then once you're comfortable at this GNU radio level, then you can see that you can make it real time, and you can test your algorithm whether it will work in practice, etc., by using this kind of boxes here.
Okay, sir. Thank you. So thing is that first I should write my codes in Python. At the same time, I have to get the hands-on practice on GNU radio. Then I should buy these dongles as you are suggesting. So these basically, what are the specifications from where I can get all these dongles, etc.?
Yeah, just Amazon. Earlier it was very cheap. Now I don't know. Maybe the US dollar market is a little different. So just go to Amazon.
Okay.
Yeah, I can show you this here, like Amazon. Just go. Just type USB dongle. Earlier it was just 500 rupees, but now things have gone a little high. So these are the dongles that you get. And see, for example, here. so USB. These are dongles for our Bluetooth things, but perhaps what you need is DVB dongles.
Okay.
And here you can see that this is DVB dongle. This is stuff that is enough to play around all this. You can see the prices are on the high scale now, but it was 500 rupees only a few years back. Maybe the dollar caught up, and so the price has gone up a little bit.
Okay.
Yeah, so we used to buy this for 500, 600 rupees outside Amazon. Or even Amazon initially was only that much. Now the cost has gone up. I don't know why. Right, so this is the kind of dongles you can just buy it, and that's enough to do all the receptions and everything. But this does not transmit though. So if your lab or college has a hardware budget, you can buy one transmitter.
Yeah.
For everybody. Yeah.
Okay, sir. Thank you, sir. Thank you.
Yeah. Yeah, my email is there. I think the next session has to start, so feel free to go and start whenever you want.
Any queries from the participant side?
Sir, one more question. Is it easy to install this GNU radio on our laptops?
Yeah.
Is there any specific is it any specific guideline or anything, any difficult part where we basically stuck in downloading or installing, or it's simple?
Yeah, in Ubuntu, Linux, etc., it is extremely simple. One command will do everything. Don't have to even worry. In a minute, you will have it. Windows, there are two options. Currently, the version available at gnuradio.org for Windows. Just download and install. Most people got it correct in the first go itself. But some people had issues with Python and Visual C++ already being installed. Not everybody had trouble. 75 to 80% of the people have it working correctly in the first go. So if you try, some configurations have an issue, but Linux completely 100% working everyone. Microsoft also, we've been able to make everybody's system working. Hundreds of systems so far we have made it working, though some 20% of the people had trouble in the first installation. Apple, we can't say anything so far because we have not managed it for Apple.
Okay, sir. I will try, then I will connect to you. Thank you.
Hello, sir.
Yes.
One more question, sir.
Please.
Sir, is there any possibility to use FPGA blocks in this GNU radio platform?
Yes.
Or only communication related blocks are available?
No. So what is happening is that this who's that fellow? National Instruments now that they have now come up with that X310. There is FPGA enabled USRPs, these boxes that I was showing. So where now there is a lot of demand. I don't know whether it's there was some talk about just like LabVIEW, because LabVIEW can do it. So GNU Radio should also be able to do it. Maybe I should, you can send me an email. I'll check with what is there in the latest script, because I bought a X310, but because of the pandemic, we didn't use it so far. So I don't exactly know at this point what are the capabilities there. Okay, something was, there were a lot of discussions in the development forums, etc. I'll check that out. Yeah.
Okay, sir, sure, sir. So from participant side, any more questions?
Any queries from the participants? Okay. Thank you, sir. Thank you for the wonderful presentation. The session was extremely informative and useful. It helps us gaining a wide knowledge in the domain of wireless communication, especially. You have broadly covered all the concepts related with wireless communication. Surely our participants have taken many valuable things from this session. So a new thing our participants has learned, the GNU radio, open source software, which will be more helpful for them for doing their research in communication domain. Thanks a lot. Even in your busy schedule, as well as even in your health issue, you have accepted our invitation and you have given a wonderful session for us, sir. Thank you, sir.
Yeah, thank you. Thank you, Dr. Yeah. Okay, bye, everyone.
Thank you, sir.
Thank you.
Thank you so much, sir. Thank you.
So participants have posted the link in the chat box. Kindly fill it.
Dear participants, feedback form is available in the chat box. Kindly fill the feedback form for your attendance. Thank you. We'll join for the session number 11 by 12 noon exactly by Dr. K.S. Sridharan from Sri Satya Sai Institute of Higher Learning, Puttaparthi, Andhra Pradesh. And the title for the session is Intelligent System for IoT and Wireless Sensor Networks.